Ready? Okay, the 45-degree angle, we indicated that the part of that horizontal, of that component, the horizontal component of the shear force is taken out by the longitudinal steel. We're able to do that because when the shear is biggest, the moment is the smallest. So we don't really need the bars, the longitudinal bars out near the end where we need it for shear. And then the vertical component is taken out by the stirrups. So the stirrups have two purposes. One is to take the shear out. Two is to facilitate the installation of longitudinal bars. Okay, now we have two possibilities with those stirrups. One is that they're spaced at code minimum. And code minimum is the effective depth divided by 2. So if I've got an 18-inch effective depth, the farthest the stirrups could be placed apart is 9 inches. It's a 20-inch effective depth, 10 inches. Okay, the only thing that will trump that is if structurally we require them to be closer. So we're going to have A is code minimum, B is structurally needed. So if I need them closer, I have to put them closer. If I don't, then code requires me to put them at D over 2. So the way it's set right now, all I've got to do is determine whether D over 2 works. If it works, I'm done. The second part is if it doesn't work, I've got some additional calculations to do to determine where to put the stirrups in order to make it structurally sound. So right now, I think what we'll do is we'll take a look at an example problem. I'll give you an idea how we go about doing this. It's relatively prescriptive. The format is going to be based on the shear and moment diagram for a simply supported concrete beam. So if I look at it, I've got a simply supported concrete beam. And if you go back to page 114 of your text and look up case 2, it'll show you a little picture of a beam with a uniform load. And underneath that picture, it has two pictures. One, which is the shear diagram, and that looks like this. And the other is the moment diagram. And the moment diagram, of course, is centered right underneath the shear diagram. And the moment diagram takes a parabolic shape, and it looks like this. So that's the shear in the moment. We are worried about longitudinal steel, the moment governs, stirrups, shear governs. So there's my picture right here. So this picture tells me what's going on internally as far as shear is concerned. So you can see it's symmetrical. Since it's symmetrical, there's no use doing both sides. I can do one side and then mirror image it to the other side, and we're all set. So this from here to here is a drawing that we're going to produce that allows us to determine the state of stress inside the beam. So if you look at your book and you go to, they got a generic page. The generic page is on page 459. I'd rather you use the one that has numerical values attached to it. And if you do that, you're going to be on page 462. And it shows you exactly the triangle that I've got there. So you'll be producing this part of the shear diagram. So if we do that, you're going to end up with something that looks like this, a triangle, just like that one was. And notice that triangle ends up going to the midpoint of the beam, since it's symmetrical. If the beam is L long, the horizontal dimension for that triangle is always going to be L over 2. Okay, so now we've got a triangle that has one dimension. What is the top dimension? That's V max. Okay, V max is the maximum shear, factored shear in the beam. So how do you get V max? Just the way we've always done it. All you got to do is determine the reactions, go up V max, go across at the slope of the rate of the application of load, go down to negative V max and close the triangle. So V max is just going to be a calculations associated with load and span. Okay, code lets us relax that a little bit. If you look at a 45-degree angle, so I've got a beam, I've got a stirrup. If I go at a 45-degree angle, the spacing of the stirrup dictates the position of the next stirrup. And 45 degrees means the critical section is going to be D over from the edge. So code allows me to come down a distance D, and that is called VU, and that is going to be the maximum shear I have to worry about inside that beam. Okay, because the rest of it's going to lay outside the beam if I use a 45-degree angle. Okay, so now I've got the load requirements. So these top two are numbers that are generated based on your shear diagram after you factor the loads. Now, this is the requirement for shear. What can the concrete contribute? Well, we indicated concrete has a compressive strength in PSI. We also indicated that the tensile strength of concrete is 0, but the beam has shear strength capabilities. So the next set is going to be based on what the concrete can contribute, and then the steel is going to pick up the remainder or code-driven minimums. So I'm going to put a line right here, just like your book has. And if you look at that line on the page, it gives you a little formula, as does it on your handout. So on your handout, VU is letter E, V max is letter B. So this is letter B on your handout. This is letter E on your handout. And then if you go down, letter F has a phi VC. So this is phi VC. Okay, if I put that there, the formula for that, and we're on letter F of your handout, looks like this. 0.75 times 2 times the square root of F sub C prime times B times D. Okay, if you look at that, there's nothing in that formula that relates anything to do at all with loading. It has everything to do with the type of concrete and the size of the beam. Type of concrete, width and depth of beam. So this is what the concrete has the ability to resist. These are what the loads putting on it. This is the resistance. Okay, code has some safety factors built into it on purpose. And code requires us, and that was letter F, to divide that number by 2. So if you look at the page 462, and you go down, the dashed line at the end of it is a formula that is exactly like I have there, except it has a value of 5 VC over 2. So if you look at right here, that's that dotted dash line. The dashed line comes right across here. And it has phi VC over 2. So if I calculate the top one, I divide it by 2, I end up with a point on my slope. And hopefully everybody realizes the slope of this line is the application of the load rate. 2 kips per foot, 6 kips per foot, whatever it might be. Okay, this is one of the critical points. We need to figure out where do the stirrups go. Here's the value right here, letter R. Letter R is where the stirrups have to extend to. So from the left end over R, the right end over R, we're going to have stirrups. So here's my beam. Here's my stirrups. So if I go from this way R and this way R, that's the limits of the positions of the stirrups. So the stirrups are going to be there. There may be a gap in the middle. It usually is. Sometimes we put them in to facilitate installation of longitudinal bars, but sometimes we don't. So if you don't see stirrups in the middle, don't be concerned. If you don't see stirrups at the end, that's a red flag. You should know that they need to be there. So I just did letter F. Okay. Now we're down to letter R, letter K, which has R next to it. I have formulas embedded into this handout. I'd rather you do it by similar triangles. So I'm going to show you how to do it without using these formulas. If you get totally lost, there's no way other than to use the formulas. I guess that's what we'll have to do, but you should be able to follow me when I do similar triangles. Okay, so we got to know where they're going. Then we got to know if the bars are big enough. Big enough is letter L. The area of shear required is based on the formula in letter L. If our bar is big enough, we're fine. If it's not, we go up to the next size. So stirrups. Stirrups typically don't wander much in size. Stirrups are typically a number 3 bar or a number 4 bar. 3 bar is 3/8 inch diameter, a 4 bar is 1/2 inch diameter. Why? We can bend them. If you notice me, when I drew them before, I drew a U or an O. So the bars have to be bent. If you get a great big bar, you can't bend them very easily. Number 3s are typically used for 8 bars or bigger or smaller. So if my longitudinal steel going here is a number 8 bar or less, we use number 3 stirrups. If it's a 9 bar or more, we typically use a number 4 stirrup. The problem statement will tell you that. You don't have to worry about it. It'll be written in the problem. So it's either going to be a 3 or a 4. If the area of steel is not big enough using a number 3, all we do is jump to a number 4. And we're all set. So there's one thing you need to know. Where do they go? They go from the left and right end over R. Okay, that gets us through that. Then the next thing we've got to worry about is, are they big enough? Letter L takes care of that. And then we got to figure out the maximum spacing. Okay? And letter N does that. So if the spacing comes out, this is called, I'm going to use S max star. The star indicating it's a calculated value rather than a minimum value. And now I'm on letter N. N2, it says S max is AV Fy D over phi Vs. Okay, AV. AV is a number you calculated in letter L. So this AV is either going to be 2 number 3s or 2 number 4s. Why 2? Take a look at picture in your text. Okay, if you go to page 460, you've got a cross section through the beam. It shows the stirrups sticking out of the beam, and notice in that picture there are 2 of them. So we've got 2 number 3s or 2 number 4 bars sticking out of that cross section. Okay, so that's that one. Fy is the type of steel. you're all set there. That's going to be a 40, 50, or a 60 grade steel. D is, if you look at it, it says on it right there, it says D is the effective depth given in the problem. D is going to be given. It's the effective depth, same as you've always done. 5 ES is the only thing you don't have now. And it's pretty simple. If you look at the picture I told you to look at, which is on page 462, they show you where that is, and that is right here. That's that dimension. And notice on the picture that's got cross-hatching in it. That's the critical section right there. Okay? That's the area we worry about. Okay, so if we've got everything, what am I going to do? This can have two outcomes. It can be less than or equal to, I'm going to go equal to or greater than. Can be greater than or equal to d over 2. Then we use d over 2. So that was my first. Remember right here I had before that we had A and B? This is the letter A. If S max calculated here is greater than d over 2, our spacing is going to be d over 2. If S max calculated there is less than d over 2, we're going to have to reduce stirrup spacing. Okay, so probably easier for me to explain this doing an example problem. So I think what we'll do is we'll do an example problem that gives us A, this guy right here first, something that works with d over 2, and then we'll move on to another sample that tells us what happens if the S max is less than d over 2. That's the hard part. That's the one that's going to give you guys some problems. Okay? So why don't we do a example problem? You're doing a couple. You're doing 13.6B and D. I'll do 13.6A, and I'm not sure I'm going to do C. I think I might do another problem for that. Okay? You want a break for a minute?